All right, everybody. I hope that you guys are having a good start to your day. This is going to be our only asynchronous meeting for the entire semester. This is our lecture number 31 for the semester, and this is going to kind of wrap everything up. There will be some topics that I give you a little bit more guidance on as the final exam, or as it pertains to the final exam. But with that said, this is going to wrap up my discussion of our membranes and lipids. Okay, so with that said, let's go ahead and kick things off. Lecture number 31. So the first thing that I want to start out with a discussion for lecture number 31 is a discussion of porins. Porins are an example of a transport protein. And if you look at this slide right here, one of the first things that you can recognize is, or that I'd like you to recognize, is we've got these kind of bands, these ribbon structures. And I'm just trying to point out a couple of them. And these are beta sheets. So we talked a little bit about alpha helical proteins as well as sheet proteins. These are sheet proteins. Now, what we have here when we talk about an example of a porin is we've got a total of 3 of them, and they're all making this kind of cylindrical shape. What we're doing right now is we're viewing from the top down. And so it's these three helical proteins, these three sheet proteins that are basically positioned. For some reason, I always think about 3 different soda cans, basically, or pop cans, or Coke cans, whatever you want to call them, that they are right next to one another. Now, this is basically the simplest example of a membrane transporter protein, and it is located in the outer membrane of bacteria, mitochondria, and chloroplasts. And one thing that you could think about to, throw it back to the beginning of the semester, we talked about how mitochondria and chloroplasts were evolutionarily kind of their own entities, but then they formed a symbiotic relationship with with what would become higher order eukaryotic cells. But that's, so bacteria as well. Now, the structure of the porin determines its selectivity. So essentially what that means is that these porin proteins could be a little bit more complicated. You could have maybe a fourth or a fifth barrel protein, in which case the space between them that I'm just shading in right here, well, that could be larger, in which case it's going to be a little bit less selective, or, with the fewer number of pores, it's going to be more selective, or fewer number of sheet proteins, it's going to be more selective. These are basically always open in the sense that a solute can travel in either direction. So basically from the interior of a cell to the exterior, or the exterior to the interior. Now, a good example of a porin protein is what is known as an aquaporin. Now, an aquaporin is a protein that moves water across a membrane. Now, that might sound a little bit odd because of the fact that water is able to diffuse across a membrane or a lipid bilayer, but think about it in the sense that diffusion is a time-dependent process, and it's going to go at a rate basically as long as it's going to be going at a rate so long as it's favorable. An aquaporin, being a protein, well, that can participate in the movement, in which case an aquaporin can move water across a membrane or a lipid bilayer at a much higher rate. These were discovered by Peter Ager. This is just a list of different aquaporin proteins. And what I'd like you to take away from this is, I don't want you to know those names, those identifiers. But instead, I want you to think about these in terms of how ubiquitous they are. So if we look down here at AQP8, We've got liver, pancreas, colon, placenta, aquaporin. EQY is within the yeast plasma membrane. They do the same thing. They move water across the membrane, a lipid bilayer. Okay, now to dissect an aquaporin a little bit more specifically, well, first of all, it's a helical protein. I'd like to draw your attention over here. So we've got a bunch of alpha helices over here. And then I'd like to jump over to the left-hand side of the figure, or the left-hand side of the slide. And what we have here is an alpha helix. And this is moving from one end of this slide, the top half, to the bottom half. Now, what I'd like to also draw your attention to is this space right here. Oh, oopsies. This space right here and this space down here. What we have is the extracellular space and the intracellular space. Now, the way that, or what I think makes this a completely fascinating protein is whenever I think about certain concepts and certain ideas in chemistry and in biochemistry, it always seems like abstract. It seems like I get the rules and I'll go along, but it's tough for me to wrap my mind around it. For instance, I know in Gen Chem 1, whenever I learned about a mole, that just blew my mind. Like 6.02 times 10 to the 23rd of something, that's just, it's such a large number that I can't even begin to process it. Now, similarly, whenever I think about charges, I think about like an ionic bond. I think, okay, well, there's a positive and there's a negative. Okay, yeah, those are going to be attracted to each other. I get it. And that's going to cause this protein, this amorphous thing, to basically establish this kind of linkage. Now, I bring this up because when it comes to an aquaporin, you have water. Now let's go ahead and draw a water molecule. And one of the first things that I know that you talk about, or that I remember talking about in organic chemistry, was, well, we really nailed down this dipole moment stuff. We got partial negative and partial positive charge. So you've got a water molecule with positive end and negative end effectively. Now, again, that was one of those situations where I was like, okay, I'll go along, I get it. Now, what I'd like you to do is think about this right here, and then think about different amino acids, okay? So we have a handful of amino acids that, well, they could be positively charged, they could be negatively charged. Now, with that said, an aquaporin is a protein that is going to move water from the extracellular space to the intracellular space, or vice versa. Now, most of what makes up this kind of manila envelope colored thing, well, this is our protein. And most of the residues along this end and along this end, there are lots of hydrophobic residues. So when you think about hydrophobic, you think, well, it's going to repel water, okay? So we've got lots of leucines, isoleucines, maybe some, let's see, maybe some phenylalanines. So you have some residues like that. And what are they going to do? Well, if we've got, let's just say hypothetically that we've got a leucine over here and a leucine over here. Well, what are they going to do? They're going to both be pushing water away from itself. So water is going to be going here. It's going to be shifted up that way. Okay. Now, what's that going to mean? This water molecule, for instance, or this water molecule, they're basically both going to be kind of, there's going to be a force, there's going to be a resistance to them. Now, what that's going to do is kind of limit their range, limit the space that they can be in. Now, the ultimate effect of that is going to be, I guess it's going to be influenced by, well, the amino acids that are in this region. I'm going to erase some of what I'm drawing over here. I suppose I can erase that. we really want to do now is focus on the amino acids within this region. Well, this will be the tightest point, the most narrow region of the protein. And what we have taking place here is we have all of these individual water molecules. So I'll draw your attention up here and then down here and then down here. What we have is, well, we have a 3 wide water kind of a 3 wide range where 3 water molecules can be. And then go a little bit further south, you get 2 wide. And then down at this most narrow region of this protein, it's only so wide as to fit 1 water molecule through. Why is that? Well, because up here, where we have 3 and 2 wide, we've got lots of hydrophobic amino acids. So they're going to be pushing water, kind of forcing them into a region. But then in this tightest region, you've got amino acids like an arginine, for instance. You've got the N-termini of different amino acid residues that, what are they going to do? They're going to have positive charges. So what are they going to do? They're going to be pulling the negative end of a water molecule. Now, this arginine and asparagine, what these 2 amino acids are going to do is they're going to separate individual water molecules. Now, this is the part that I can visualize for my own purposes or for my own sake, and I hope that this is relatable. I can visualize a water molecule. And whenever I think about a solution or something, I just think, well, there's more than you could ever imagine. You've got hydrogen bonding where, you have basically this complex network. Well, what we're doing within this region right here is we're going from that complex network of water molecules, and we are putting 1 water molecule behind another, behind another, behind another, so that we can basically shoot those water molecules through one at a time onto the intracellular side of the cell, or the lipid bilayer. And this is all because of different amino acids. Now, one of the things that I've talked about quite often this semester is I've always tried to talk about like mutations. What if you had a different type of residue here? So if we took this region right here, where we already said that there are a good number of hydrophobic residues, what if you put something like a serine in place of a leucine or an isoleucine? Well, serine's really good at hydrogen bonding. So let's say you had a mutation of a leucine to a serine over here. And then over here, you just had a leucine. Well, what's this leucine going to do? It's going to push water. It's going to repel it. But then the serine that's over here is going to say, wonderful, I love water. I love having water around. So it's going to attract it. In which case, what's going to happen to the flow of water molecules through this aquaporin? It's going to be slowed down tremendously, because rather than water molecules being kind of forced to run through, instead now you have something that's attracting that water and basically establishing a hydrogen bond with it. And so it's not going to work very effectively at really shuttling it through. Okay, so another type of protein, another type of important protein is an ion channel. Ion channels are generally, or are going to be very specific for sodium, potassium, and chloride ions. Now I'll take you back to Gen Chem 1. What makes those different? Well, in one case, you've got an anion, the chloride, but then the sodium and the potassium, well, they're different sizes, okay? So potassium channels are 10,000 times more permeable to potassium than for sodium. Will a potassium channel move sodium across? It will, but it's going to be less likely to move it across. Now, sorry, how does this actually take place? So what the, potassium channels maintain a diffusion limited rate of 10 to the 8th ions per second. So it's moving it pretty quickly. Now, to visualize more or less the flow of a potassium ion through one of these channels, what does it look like? Well, I'd like to draw your attention down here. We've got a potassium ion on the interior in the cytosolic space moving to the extracellular space, so moving out of a cell. We've got our lipid bilayer right here. We've got our ion channel protein. Potassium is going to basically, as a positively charged ion, be attracted to the negative ends of water molecules. Now, what these are going to do is they're going to position the negatively charged oxygens near the potassium ions. They are going to move them toward basically the binding site for potassium within the active site of this protein, or within the space in which potassium gets loaded on and moved all the way through. Now, what we have here is we have these carbonyl oxygens. That's what these red circles are representative of. So these say backbone carbonyl oxygens. They form a cage that potassium fits potassium precisely, replacing waters of the hydration sphere. So this is our hydration sphere that we formed. We had 4 water molecules that helped form that. Now all of a sudden, what's going to basically get this green sphere, which is our potassium ion, to jump into this blue space right there? Well, these, which I'm circling in red, these carbonyl oxygens of our backbone is going to do that. So I know that whenever we've talked about mechanisms, we've generally talked about different amino acid R groups basically doing all the work. Like an aspartic acid has lone pairs of electrons, so those electrons can be involved in, establishing a covalent bond or something like that. We don't really talk too often about the backbone. However, in this case, what we have is backbone carbonyl oxygens that are displacing water molecules in favor of binding this potassium ion to load it and to basically funnel it through so that ultimately it can get to the other side of the membrane and be released, where those carbonyl oxygens are then, well, it's kind of a cycle of life sort of thing. Those carbonyl oxygens are going to be replaced by waters that form the solvation sphere. So that's kind of what we have going on here. Next up are ion channels that are gated. So ion channels that are normally closed or open. They are normally closed and open transiently to perform specific tasks. Opening and closing is known as gating. Gating occurs in response to a variety of stimuli. These stimuli can be any number of things. They can be touch, sound, presence of something like oxygen, or they could be a physical stimuli. Ligand-gated ion channels require the binding of an extracellular ligand, such as a neurotransmitter. Signal-gated, binding of an intracellular signal, like calcium. So here's our difference. We've got an extracellular ligand would be ligand-gated, whereas intracellular, we're talking about a signal-gated channel. Voltage-gated, observe changes in membrane potential, which is what we're going to wrap up this lecture with. Now, examples of a ligand-gated channel would be something like the nicotinic acetylcholine receptor. This is found at a postsynaptic cleft, and binding of the molecule acetylcholine opens. So here's our acetylcholine way up here. whenever acetylcholine is bound, then it opens up and allows sodium ions to go through. So our protein is right here. We have these 4 helical proteins, or these 4 helices. And what we have there is we have ultimately 4 helical proteins, which make up one of these subunits. We have a total of 5 of those. So that would be the better part of 20 alpha helices that are wrapped up together. So we have 4 helices that make up 1 helix, or that make up 1 subunit. And then we have the alpha, beta, or alpha, beta, sigma, and gamma subunits. So we have these 5 subunits. And what 2 of them have is they have acetylcholine binding sites. Okay. Or sorry, what they all have is acetylcholine binding sites. Now, whenever the channel is closed, here is kind of our representation of it. If you look at this, the contacts between every one of these individual subunits, well, they're not in contact with one another. However, when 2 acetylcholine, there are only 2 acetylcholine binding sites. When 2 acetylcholine bind to those 2 binding sites, which are reflected right here, here and here, whenever acetylcholine binds, then this protein undergoes a conformational change, which causes this M2 helix to rotate, which causes these larger, more complex structures to ultimately rotate. And that causes the central cavity to open up, which enables sodium ions to flow through. Now, there are many neurotoxins and chemical nerve agents affect either the binding of acetylcholine or act as acetylcholinease inhibitors. So what that could mean is that this channel is left open, or basically it's never able to be opened. Now, another example of one of these transporters is a glute transporter. So this is an example of a carrier protein which undergoes a conformational change upon binding glucose. Glute 1 through 4 are transporters that are highly specific for glucose. So what I mean by that is that they're going to bind glucose over something like galactose. Now, Glute 5 is a transporter protein that is highly selective for fructose. This allows glucose to bind on one side and be deposited on the other. So we've got glucose on this side of the membrane, and we need it to get onto this side of the membrane. So glucose rolls in, binds. Then our protein undergoes a conformational change. The open end right here is closed off. And therefore the closed off end, well, that opens up. And what does that allow? That allows the glucose molecule to move on to the other side of the membrane. Okay, so once glucose is released, it dissociates, well then this open end of the protein closes off, the closed off end of the protein opens up so that we can begin this process all over again. Active transport, energy input drives transport. Some transport must occur such that solutes flow against their thermodynamic potential. Energy input drives that transport. So an energy source and transport machinery can be coupled or are coupled with one another. So here what we have is primary active transport. Now what we're doing is we're moving this molecule X across this membrane. So it's going from the interior to the exterior. So it's going from a low concentration to a very high concentration. So that's an unfavorable movement. However, when we combine the movement of this substance from a low concentration to high concentration, we can combine it with hydrolysis of ATP to release inorganic phosphate, also known as PI, and adenosine diphosphate, also known as ADP. So it's this ATP hydrolysis that says, okay, we can move against this concentration gradient. Okay. Now, our secondary active transport. Here what we have is we've got two different substrates. We've got substrate S, we've got substrate X. S needs to move across the membrane from a low concentration region to a high concentration region. Okay, so that's an unfavorable movement. How does that take place though? Well, we can move this molecule X from very high concentration to a very low concentration. That's a favorable movement. So this protein right here takes X and S, moves them both across the membrane, and releases them onto the interior of the cell. One of those is a favorable movement, the other is not a favorable movement. But this kind of presents a chicken and egg sort of discussion. We've got X on the interior of the cell where there's a low concentration. Then we got a ton of it on the exterior of the cell. How are we actually going to do that? Well, we're going to use ATP hydrolysis in order to drive that. So we're going to hydrolyze ATP to make ADP and PI, moving X from that low concentration to the high concentration. So the movement of X is going to be driven by ATP hydrolysis. That will make it work. So that will give us this large volume, or this large concentration, this high concentration of X on this side of the membrane. And then we can use this other protein right here to move X and S across the membrane. So they're coupled together. So we have ATP hydrolysis coupled with transport of X, and X and S transport coupled. Movement of S is unfavorable, movement of X is favorable. Now, ATP hydrolysis is one example of a type of reaction that can be used to couple with an unfavorable reaction, but it doesn't have to be. So you could use ATP, you could use light, or you could simply use a concentration gradient to do that. So to kind of get into this sort of question, to probe into a slightly more specific example, we have a sodium potassium ATPase. Okay, so the net for this reaction is right here. We have 3 sodium ions that are going in, 2 potassium ions that are going out, and ATP, H2O are involved. And what is going to ultimately be released is 3 sodium ions are pumped out, 2 potassium ions are pumped in, and we get ADP and PI. So this is going to maintain a low sodium concentration intracellularly and a high potassium concentration. Okay, so here's ultimately what we're looking at. We're looking at a cytosolic concentration of potassium ions of 140 millimolar, and sodium ion is 12 millimolar. Okay, our extracellular fluid concentration is 4 millimolar potassium and 145 millimolar sodium. So we're taking sodium from 12 millimolar to 145 millimolar. Okay, so this right here, to get these sodium out, that's kind of tough because low concentration to high concentration. Potassium, on the other hand, well, potassium is going from 4 millimolar to 140 millimolar. So we've got two kinds of, like, we basically have a SIM-porter, an anti-porter, I'm sorry, that is moving two things in unfavorable directions. This is, however, crucial for all organs, but especially for neural tissue and the brain. ATP hydrolysis is going to drive potassium out, or sodium out, and potassium in. So we're using ATP hydrolysis in order to do this. Now, this is an anti-porter protein, so because we are moving two things in opposite directions. We've got 3 positive charges exit for every 2 that enter. Now, all cells expend a large fraction of their ATP to maintain the required cytosolic sodium and potassium concentrations. Okay, now that's kind of the overview. This, I think, is a really interesting schematic of what we're observing. The first thing that I'd like to draw your attention to is right here. A Spartal phosphate residue. Okay, so we have talked about post-translational modifications. Post-translational modifications. So if we think about that word a little bit, post-translation. After translation, there's a modification. What this is showing us is the N termini and the C termini of the amino acid aspartic acid, CH2. Normally, there would be C double bond O and then O minus. But that's not what we see here. We don't see this minus, O minus. Instead, we see an OPO3, okay? So this is kind of unique because generally when we've talked about post-translational modifications, especially a phosphorylation, we see a phosphate group on something like a serine. In this case, we don't, okay? So that's just sort of an interesting thing that I'd like to point out. Now, what I next want you to do is think about, okay, what are we doing? We have the inside portion of the cell and the outside. What we are doing is we're taking 3 sodium ions and we're putting them out. And then we're taking 2 potassium ions and putting them in, okay? Now, the key to all of this is centered around that amino acid, that aspartic acid, in the phosphorylation of that aspartic acid. So we've got these 3 sodium ions. We have our enzyme E1 in its initial state. That is bound to our 3 sodium ions. What that is going to do is it's going to bind ATP. Whenever E1, the initial form that our enzyme is in, has bound ATP, it's also bound 3 sodium ions. Now, what it's going to do at this point in time, it's going to transfer one of those phosphates from ADP onto itself, onto an aspartic acid, which is single letter code D, on E1. Okay, so this enzyme becomes phosphorylated. At that point, it can undergo a conformational change. The sodium can be transported to the exterior side of the lipid bilayer, and subsequently, that sodium can be released outside of the cell. Okay, at this point, our enzyme is still phosphorylated and now can bind to our 2 potassium ions. So those 2 potassium ions can bind to our phosphorylated enzyme. Now, this phosphorylated enzyme is then dephosphorylated. The phosphate is hydrolyzed away from our enzyme, in which case now we have the dephosphorylated enzyme, which will bring the potassium ions to the interior side of the cell. So we have this phosphorylation event that takes place that enables a conformational change that allows the sodium ions to be transported outside of the cell. So the way that I always like to think about this is a phosphorylation triggers the conformational change that releases the potassium with the sodium on the exterior of the cell. But then that dephosphorylation enables the binding of the phosphorylated form of the enzyme is able to bind to the potassium. Dephosphorylation then brings that potassium on the inside of the cell. So ATP phosphorylates our protein only in the presence of the potassium, the sodium, and the Spartal phosphate residue is then hydrolyzed only in the presence of potassium. So ATP hydrolysis, the enzyme's dephosphorylation takes place only in the presence of potassium. The ATP transfer of a phosphate to our enzyme occurs only in the presence of sodium. So E1, that form of the enzyme, has a very low affinity for potassium. That's actually the form of the enzyme that releases the potassium, but it has a very high affinity for sodium. Now, E2, on the other hand, has a very low affinity for Na, but a very high affinity for potassium. So that E1, E2 is basically different forms of our enzyme. It's the same ATPase, but what is it binding to? Okay. So the last thing that I wanted to talk about today, was transport across a membrane. So diffusion of a substance between two sides of a membrane, the dynamic resembles a reaction. So we have our substance moving from the source to its destination. The difference in the concentration of a substance on two sides of a membrane generates a chemical potential. So we see that as delta G equals RT ln, and then basically KEQ, A concentration at our destination over A concentration at our source. Now, the movement of ions across a membrane also results in a charge difference, generating electrical potential difference, in which case we see that displayed as Z sub A times Faraday's constant times delta psi. Now, all of those illustrated, Z sub A is the charge of an ion, Faraday's constant is displayed right here, and delta psi is membrane potential, units for volts. So those two things are combined together to basically come up with, well, what's the free energy change of a substance moving across a membrane? We come up with this electrochemical potential. We're relating the chemical potential as well as the electrical potential of that substance. So whenever you talk about a membrane potential, you have to talk about the electrochemical potential. By default, delta psi is measured as the potential inside the cell minus outside the cell. So we are looking at inside versus the outside. Now, a negative number indicates the inside of the cell is more negative than the outside of the cell. A positive number is going to show the opposite. But if an ion moves from the outside to the inside, then the potential is just fine. Whatever value that you're given, you do not change it. So if the problem describes movement of something from the outside to the inside, you're not going to change that. You're not going to change that symbol or the value. If an ion moves from the inside to the outside, so if Na, for instance, to visualize this, is going from here to here, from the inside to the outside, then you have to change that delta psi value, whatever it's reported as. So what I want you to think about is if it's going from the outside to the inside, out, in, then don't worry about the sign. Almost always, the cytosol is considered the inside of the cell. Additionally, if more than one ion is transported, you need to calculate the free energy change for one ion, then multiply for additional ions. So the question here is it favorable from a charge standpoint to transport chloride ions into a cell when delta psi is equal to negative 60 megavolts or millivolts, sorry. Now let's think about this question. This question is it favorable from a charge standpoint to transport into, okay, we've been given a delta psi value. Do we change the value? I gotta write E and then question mark. Do we change that? Well, let's see. If we're going from the outside in, so this would be outside to in, no change. So this delta psi would be a negative value. Okay, so then the question is it favorable from a charge standpoint to transport chloride ions into a cell when delta psi is negative? Okay, so now what we need to do is we need to come up with, well, What is Faraday's constant? Well, that's a constant, so we don't really need to worry about that. But Z sub A, that is our charge of our ion. So Z sub A would be negative. Okay, so we're moving a negative times Faraday's constant times, well, that's a negative value. So that would ultimately be a positive value. So delta G here, just from the electrical potential, would be positive. So no, it would not be favorable. What about transporting it out? So doing the opposite. Yes, it would be. Okay, so let's get down to this sort of practice problem. This one is looking at our equation, delta G equals RT ln KEQ Z sub A times Faraday's constant times delta psi. We're transporting sodium ions in or out of a cell when delta psi equals negative 60 millivolts. Our cytosolic concentration is 12 millimolar. Our extracellular concentration is 145 millimolar. What is the change in free energy associated with transporting sodium into, put a little plus there, sodium ions into the cell at body temperature of 37 degrees Celsius? Okay, so that's one thing that we got to change. We got to add 273.15 equals 310 Kelvin. So our temperature there is 310. Okay, now this shows us our chemical potential. So our R value. So just looking at the chemical potential, this guy right here is our R value. This guy right here is our temperature. And then our destination over our source concentration. We are going into a cell. So our destination is the cytosol. So that's where we get this 12. Our source is extracellular, 145 millimolar. So from a chemical perspective, this has a delta G of negative 6.42 kilojoules per mole. So favorable. Now, there's kind of a simplistic way of looking at it. Electrical potential. Let's see how things change. Okay, so the first thing that we have to do is Z sub A. Okay, that's positive because we're talking about a sodium ion. Our Faraday's constant, well, not our Faraday's constant, but Faraday's constant right there. Now, our voltage. We're going from millivolts to volts, so we see negative 0.06 volts. And ultimately, that's a positive times a negative gives us a negative. So that would be also favorable. So our electrochemical potential is going to be negative 6.42 plus negative 5.79, which gives us a total delta G of negative 12.21 kilojoules per mole. Okay, so how could this problem be different? Well, one way that it could be different is if we're going out. So how would that change our chemical potential? If we're going out of the cell, well, then this right here gets flipped, 145 divided by 12. Okay, so that would give us a negative value there, in which case, basically, that would make that an overall positive value. Okay, next up, well, if we're going out, we'd have to look at the electrical potential difference. We would have to switch this value right here. And so that would mean that this would be positive. So that would mean that we're talking about positive 5.79 kilojoules per mole. So then ultimately, we would come up with that, a positive 12.21 kilojoules per mole. So whenever you're confronted with this sort of problem, what I want you to do is I want you to think about it in terms of, okay, breaking it down into these two different parts, part one and part two. And how do part one and part two combine together? Okay, so we're talking about transporting ions. How would this be different if we were talking about transporting something like glucose? Well, let's think about the charge of the ion glucose. There's a fundamental problem with that statement that I just said. Glucose isn't an ion. Glucose does not have a charge. So does glucose have an electrical potential? Does not. It would be zero. Chemical potential difference? Absolutely. You can calculate that all day, but there's no electrical potential difference. So keep that in mind. This is always about ions. If you're talking about a +2 or a +1, well, you've got to consider that right here. Then the rules that we said just on the previous slides about delta psi values. Do you change the value or do you not? In this case, we're talking about transporting into a cell, into the cell. So we are not changing that value. If we're going out of the cell, then we change that value. All right, well, I hope that was helpful, and I hope you have a wonderful day. Let me know if you got any questions.